Okay, take two. Maybe it'll work this time. I don't know yet. Yeah, I think that this time it works. Now I understand there's a state machine in YouTube's thing. Anyways, whatever. We're live. It's day 5. We're going to practice linear algebra today, which I'm excited for. Thank you for tuning in. We're going to continue this book, Shilov, which we started yesterday. So I'm going to take a moment to just review a couple of I'll review one concept that we introduced yesterday, determinants. And something I love is that I was wrong yesterday. I said something that I thought was going to be true, and there was a slight part of me that was like, I'm going to double check this later. And it turns out I was wrong. I confidently said that a determinant was not 0, but it actually was. And I love this because it's now an example that I will never forget because I made that mistake publicly, live on YouTube, and I will always remember this, which is super cool. It gives us a great motivation and opportunity to introduce the idea of linear combinations of rows in a matrix. I'll explain that a little bit later. So this stream, everybody is new to it because it's a brand new channel. This stream is the idea of a math practice stream. So I am just going to be live doing math, practicing math, and I am the farthest thing from an expert. I am not a professional mathematician, so do not trust me. Do not learn from me. You can learn along, but consider me more like a peer in a study group as opposed to an expert and a teacher. But I hope that we can all learn from one another, and I think generally things I say are generally going to be true, but there will be many mistakes along the way, which is fun. So here's a fun mistake that we made yesterday, and we're going to fix it. A cool thing is that we are also going to review this fact from number theory 2 or 3 lectures ago. Lecture is the wrong word. Practice streams ago. 2 or 3 days ago or something. In particular, I did this one in days... Today's day 5, so then we did this in day 2 and day 3. We introduced determinants in day 4. I think that today is day 5. We'll find out. And the reason that I'll be reviewing 1 plus ... n, we're going to use that, spoilers, in this exercise, which is great. And then always a goal is to just hang out, and if there's nobody to hang out with and chat with, then I'll just be live learning, and we're just going to be live solving problems from this book and taking notes from this book today. A goal of all of these streams and my entire channel is that I want to make math a little bit more accessible to everybody. I want all of these streams for anybody to be able to get something from it, whether or not you're studying at the level of math that I am. And a great thing here is that I'm revisiting math, everybody. Like, I studied math like 15 years ago or something. I'm getting old, and now I want to rebuild my passion and love for math. So, we got to dust off some cobwebs. Like, this machine is pretty rusty, but we're going to get back in shape. So I want to be able to explain a lot of these concepts to a wide audience, including to kids or to adults who have never seen math, like this kind of math before. So let's get started. First, what's a nice color to use? White is like a little loud, right? Like, how about this color? I think that's a nice color. Blue on black, is that? I don't know. You all tell me. I think it looks all right. So let's review. Yesterday we introduced the idea of a determinant in order to solve determinant. I think it's spelled something like that. We introduced the idea of a determinant, and it's a great tool to solve systems of equations. We gave an example of a two-equation system. In particular, everything when we're working on linear algebra, we're always talking about lines. You know what? I do want to switch to white. White, it's a little too bright. I think if we made it just a little thinner, I don't know. I'm going to tweak the colors as we go. Let's stay with blue. All right, so in particular, we are talking about lines whenever we're working in linear algebra. Let's get something that pops a little bit more. So we are talking about lines and whether or not we can find a solution to two equations. We're not always able to solve a system of equations because, for example, this one, this one here does not have a solution. It's two parallel lines that will never cross because we are in Euclidean geometry. And in Euclidean geometry, parallel lines never cross. Another type of example where this one has, this one has zero solutions, right? And then maybe this, it's just another line that overlaps. It's like two equations that mean the same line. That can happen. You can have two equations that produce the same line. This one would have infinite solutions. But then the case that we want to be in is this case where there is one solution. I guess for either of these lines, we have a solution here, and we have a solution here where they cross. But we're focused on that first of the two cyan lines. If there's one solution, there is one solution if and only if. That's what this double arrow means. It means if and only if the determinant is not zero. Okay? So we introduced the idea of a determinant in this way. I explained that a determinant is something special that you can calculate to tell us whether or not a problem is even solvable to begin with. That's really useful because why waste all your time trying to solve an equation, a bunch of equations, especially when there are not just two, but like 200 in 200-dimensional space? Why try to solve that if you know that it's not solvable at all in the first place? Like, if the determinant is zero, stop wasting your time. There's no solutions, or there are infinitely many solutions. So that's pretty neat, I think. Cool. So I want to come back to the examples that we had yesterday. The simple example, and again, this is kind of like at the college algebra or algebra 2 in high school, algebra 2 or college algebra. College algebra would be just like a slightly harder version of this, but it's still essentially the same. We have two lines. Y1 equals, what did I use? 2x plus 3. And then y2 equals, you know what? Yeah, y2 equals 4x plus 5. Let's keep those little subscripts. This is just reminding us that x1 and x2, these are just in two different equations, but there's nothing super special about that. They are still just the regular equations like y equals mx plus b. Don't get confused about the fact that there's a subscript. So I kind of actually want to just erase. Okay. I'm still getting used to this app. It's a really lovely app, though. Highly recommend. What is this? Notability? It's a really lovely app. Yeah, I don't want to make this confusing, so I want to, let's just say y equals 2x plus 3 and y equals 4x plus 5. The game is, can we find xy that works or solves both? So this is still the easy part of the video, but then we're going to get more advanced as we go. So if you're somebody looking for more advanced math, just skip ahead and we'll try to get a little bit more advanced. All right, so one degree of sophistication that I wanted to add to this is we could rewrite this as negative 2x plus y equals 3 and negative 4x plus y equals 5, right? All I did was just subtract 2x from the first equation, and I subtracted 4x from the second equation. Now, here, in this problem, last time I just jumped straight to the idea of a matrix, and it may have been confusing. How do we get from those simple equations that we had to the matrices that we were working with? And I kind of did a lot of hand waving. This matrix on the left-hand side would be negative 2, 1, negative 4, and 1. So, in a sense, it's kind of like we're saying, okay, this is just extra information. We already know that we're working with x and y, and that we're adding a number here. All that we really care about are these coefficients. There's an implicit 1 above in front of those y's, right? So it's kind of like, let's get rid of that unnecessary information and just focus on what really matters. It's these coefficients. Now, this is solvable. So I said that something was not solvable, but this one is. We ended up finding by substitution that we can substitute y equals 3 plus 2x. We can kind of plug that into the second equation. Let's switch to a different color maybe. And we've got negative 4x plus, now we're going to substitute this, 3 plus 2x. We replaced the y in the second equation with 3 plus 2x. And we know that all of this equals 5. Yeah, so this is just review. We end up getting negative x equals, subtract 3 from both sides, and we get 2. Is that? Wait. No, I'm bad at math. Negative 4x plus 2 is negative 2x. Negative 2x equals 2. X equals negative 1. I'm joking, I'm not bad at math, I'm just, silly little mistakes happen to everybody, is my point. Now, we do the same trick and we substitute it back into our previous equations. We had maybe in this equation y equals 3 plus 2x, we can now substitute x equals negative 1 back into that old equation. Y equals 3 plus 2 times, we're substituting negative 1. 3 times 2 times negative 1. Again, this is math for everybody, and I think people remember, if you've seen this before, this type of math you may have done previously in Algebra 2 or college algebra, and you solve a lot of these by hand, and it takes a bunch of steps, it takes like a lot of space on your page, etc. Well, what if I told you that there is a really nice way to calculate this using this fancy notation? So basically, we solved the problem here. Xy equals negative 1, positive 1. Voila, we are done. This is what we were looking for. Cool. So, now, what if I told you that we could solve that problem in way less space, or in like a nicer notation? Because I mentioned that all we really care about are these coefficients. Then in some way we should also have these numbers. Negative 2, 1, negative 4, 1. What we do is we write it like this. Negative 2, 1, negative 4, 1, where the variables are x and y, that this equals the solution 3 and 5. Okay, neat. That sounds interesting. We can take this a little bit further and write this as negative 2, 1, negative 4, 1, and whatever our variables are named, doesn't matter, we could call that A and B, or alpha and beta. We could give any letter to those variables, so it doesn't matter. We just want to solve for negative 1, 1 to be the solution. So I'm even going to take out that xy, and now we're going to write this as 3, 5. So this is a special fancy matrix that has the solution or the equation written into it by using this bar line. Now here's the game. We want to do a bunch of changes to that matrix until we get to this. The goal is to transform that original matrix into this new matrix. 1, 0, negative 1, 0, 1, 1. If we can get there, then this means x equals negative 1 and y equals 1. There's a y, there's the 1. Neat. Okay, how does that work? Let's do it together. -2, 1, 3, 5, -4, 1. Yeah, -4, 1, 5. Okay, so what I'm going to do is I'm going to keep adding and subtracting the rows from one another. If two equations are true, then when you add the two equations together, that's going to be another equation that's also true. In a sense, that's what we're doing here. We're like subtracting one version of the equation from the second. Let me make that a little bit more explicit. We started out y equals 2x plus 3 and y equals 4x plus 5, I believe. Then we also know if we add these by columns, 2y equals 6x plus 8. That is also going to be a true statement as well. Or, maybe more interesting, we could subtract the two. So this one would be the first row minus the second row. And this other option was the first row plus the second row. This one's going to be even more interesting because we can get rid of y by subtracting the second line from the first. We're going to know y minus y is 0. If we subtract the second line from the first, then we get -2x, subtract 5 from 3, minus 2. Now this is pretty easy to solve. 2 equals -2x, and now again, x equals -1. So you see how we eliminated a variable by subtracting an entire equation from the other one. That's super useful and super, super cool. This technique also, I believe, this technique is also taught in college algebra. And probably, I think you probably also see it in high school algebra too. So let me take a short little coffee sip. There's a saying that mathematicians are machines that turn coffee into proofs. That's certainly true for me. I drink a lot of coffee. I don't know how many proofs I do, but I do drink a lot of coffee. Okay, so this is pretty cool. Okay, this maybe is a little bit more useful. Maybe I'll just do this all the time, but it does still take up a decent amount of space, and we are still repeating a lot of information. So imagine, like, what if we didn't just have x and y, but we had x, y, z, or a, b, c, d, e. Like, maybe we have many variables. Maybe we have 1,000 variables that we're calculating all at once. Like I mentioned in the last video, AI is really operating. AI is linear algebra in a very high dimensional space. So I was saying a quadrillion space. That's not completely inaccurate. The AI models are trained on, like, you measure how big a AI model is. You measure how big it is based on some term that I'm forgetting right now, but like they're the weights of a matrix, or they're the weights of a neural network. It's the parameters. Yeah, so you talk about, like, the newest models are multiple billions of parameters. So literally, like, billions of parameters. Like, these artificial intelligences are doing linear algebra with a billion variables with a B. So you wouldn't want to do that by hand. You would just run out of letters. we only have 26 letters. So we're 20, yeah. Let's move on. This notation is going to work way better if you don't care about the names of the variables and other things like that. We can just keep subtracting rows from one another or adding rows to one another in order to solve this matrix. So remember that our goal was to get a 1 in the bottom right. So again, let's subtract. What I want to do this time is I want to subtract the first row from the second. So what I'm going to do is, let's say this is the second row minus the first row is now going to be this step that we're doing right now. Second row minus the first row, and we'll leave the first row alone. But now we're replacing the second row with R2 minus R1. Wait a minute. What am I doing? I misspoke. I apologize. We want a 0 here, and we can get a 0 there if we subtract the second row from the first row or the first row from the second row. But what I'm doing is I'm getting a 0 in that spot. So I try to keep things simple and do the subtract the second from the first is easier for my mind. So -2 minus, first, that spot, as I just said, 1 minus 1 is 0. 1 minus 1 is 0. That is what we're trying to get. Now, -2 minus -4. If you subtract a negative, then you add. So this is 2. Hey, stand strong. Good to see you again, man. How are you? And no worries about being late, ever, ever. No worries if you miss a stream and you watch the video afterward. But if you could do me a humongous favor, hit the like button, like right now. That would help me a lot. Because then with more likes, then YouTube shows the stream to more people, which is great. That's what we're looking for. I am fine, sir. How are you? I'm doing really good. Since you're here, here's the agenda. Day 5, we're doing more linear algebra today, and we've got a fun thing. We're going to fix a mistake that I made last time, which is delightful. I love making mistakes because then I learn that and I'll never make that mistake again. So thanks for the like, dude. Thank you. All right, so right now we're coming back to this example that I came up with last time. Y equals 2x plus 3 and y equals 4x plus 5, and we're doing this kind of game of two lines that intersect somewhere, and we're trying to find where they intersect. But I just showed that this takes up a bunch of space, in a sense, and there's a nice notation that we can use called a matrix. That, in a sense, we can stop repeating ourselves. Like, we don't have to keep repeating x and y and plus and equals. We can write x and y just one time here, and this means -2x plus y and -4x plus y equals 3 and 5. Cool. So, and we can make this even shorter. Like, if we don't care what the variables are named, all we care about is the solution is this. We could call it A, B, C, D. We could call it alpha, beta, gamma. We could call it whatever we want. The number that we're looking for is -1, 1. Cool. The pair of numbers. And then I was just explaining that instead of substitution, you can subtract and add rows from one another in order to eliminate variables. Like, this is what we're doing. We're eliminating variables. Eliminate by adding and subtracting rows. So if you add two equations together, you get another equation that is also going to be true. If you subtract rows from one another, that's just like adding the negative version of an equation, then you also get another equation that is true. So if we subtracted these two rows, we got rid of the y here. We subtracted a y from a y, and then 2 minus 4 is negative 2. But this still takes up a bunch of space. So we can do this in a much cleaner, more short, succinct way, so that our computers can make us a lot of money. So that computers don't have to do a lot of work. We want to make it easier for the computers to make us a lot of money. So I'm subtracting this, I'm confusing myself so much. Yeah, I misspoke here, or I changed my mind. Now we're doing R1 minus R2. Negative 2 minus negative 4, subtract a negative, and you get a positive. So that's positive 2. 1 minus 1 is 0, and now 3 minus 5 is negative 2. And maybe let's keep things simple and let's just keep this equation as it is. Now, I'm going to divide the first equation by 2. We're taking half of the first line now. Because, and this is just like solving 2x equals negative 2, you can divide both sides of that equation by 2. Like, if you multiply an equation by a number, you get another equation that should also be true. So here we have 1, 0, negative 1. And voila, we solved the first part of the game. We're trying to get to this matrix. 1, 0, 0, 1 equals negative 1, 1. That's what we're trying to get to. And so we're perfectly on our way. We've solved the first row, which is great. Any questions? That new equation coincide each other. Yeah, I think so. So, yeah, like when you divide, like it is the same equation. It is still the same equation. So this here, quite literally, like if we treated it as a function, x equals negative 1 is this line, x equals negative 1. But then if we said that we had another equation, 2x equals negative 2, it's the same damn line. Like, it's like that meme, like, when you look at the two images and it's like, it's the same image. Like, that's from The Office, right? So, those are the same line. It's just a different way to write that same line. Now, let's finish solving this. 1, 0, negative 1. Let's keep... I'm just doing one operation at a time, but when you get better at this, you could do multiple at once. Now, what we can do is add... we're going we're going to replace the second line with 4 times the first row added to the second row. So I'm going to add 4 copies of the first row to the second row. We have 1, 0, negative 1. Negative 4 plus 4 is 0. 1 plus 4 times 0 is still just 1. Now, 5 plus 4 times negative 1 is the same as 5 plus negative 4. 5 plus negative 4 is 1. Boom! Awesome. We are good at math. I got the right answer here. This is exactly what we wanted. This means x, y equals negative 1, positive 1. Cool. Cool. Let's take a sip of coffee to reward ourselves. And now we're going to show why I'm bad at math and the mistake that I made yesterday. And I think it's super cool because I'll never make this mistake again. I love it. Like, I love making mistakes because then you know, that's the best way to learn. Like, speaking yesterday about the theory of practice and how to study math well, make more mistakes. Like, that goes hand in hand with do more exercises, make more mistakes, and learn from your mistakes. You can't learn from only succeeding. You have to make mistakes in order to really learn well, I would say. Cool. So, yesterday's delightful mistake. I like simple smileys. Same mistakes loves to come in my solutions. Yeah, it happens, and that's okay. Like, don't beat yourself up about it. Don't be sad about mistakes. It's a good thing. That means that you're learning. As long as you learn, if you keep making the same mistake, then maybe you should read it a little bit more carefully and try to do it a little bit better. Anyways, whatever. No matter what, no stupid questions, no stupid mistakes, etc. Okay, so I'm kind of jumping around a little bit, but yesterday I introduced the idea of a determinant, and I had this matrix. And this was to solve the problem for my advanced linear algebra book that we were working on. And I'm just going to jump right to, I can see this matrix and see that this is going to be 1 times 5 times 9 plus 2 times 6 times 7 plus 3 times 4 times 8 minus, this time now I'm going to do the bracketing. Let's see. 249 plus 357. I'll review how I'm getting these numbers in a second. Wait a minute. Okay, I do need to write it sometimes just to make sure I'm not doing something dumb. Oh, yeah, okay, so if we moved it over, then it's 168. I don't know why that just gave me a lot of trouble. 168, I think, right? Yeah. Oh, 357. 249, 357, yeah, 168, yeah. or 357, 168, and 249. Yeah. Yeah, I'm just like I'm pretty rusty sometimes. But this, again, last time, what I said was pretty sure this is not 0. And the reason that I thought this is probably not 0 is because I made up this matrix. Random. Quote unquote random. I just pulled it out of thin air. Pulled it out of my ass. And generally, if you make up just a random example, you're not going to come across this special occasion. Like, if you just draw two random lines, quote unquote random lines, they're probably going to be different lines. So it's unlikely that you're going to come up with one of these problem cases, like two parallel lines. Well, I accidentally came up with two parallel lines, or really, I came up with two of the same line. And we'll see how cool that is. So let's just this time actually, I think it's coming to 0. It is. 5 times 9, 45 plus 2, 6, 7 plus 3, 4, 8 minus 2 times 4 times 9 plus 3, 5, 7 plus 1, 6, 8 is indeed 0. So I did write these numbers correctly. Exactly. So that was the mistake yesterday. It actually is 0. Mind blown, right? That's cool. So I came up with a random matrix, and I was too lazy to type it into the calculator, and yes, it is indeed 0. So connecting what I was just talking about with this, something that's great is I'm going to claim that the determinant of a matrix A is 0 if, and I think if and only if, one row is a linear combination of the other rows. This is what I remember. I could be wrong. There might be some cases that I don't remember, but I'm pretty sure it is an if and only if on this. The determinant is 0 if, it definitely is 0 if one row is a combination of the others. What do I mean by combination? Again, that is these types of combinations. Like when you add and subtract rows from each other, like, is there a way to rewrite one of the rows as a multiple of the others? I'm going to give you a second, Stand Strong. Do you want to try? Tell me, do you want to try to find it? Like, can you see how you can combine the first two rows to equal the third row? Let me know if you want me to just move on and just keep going, because that's okay. Please repeat the question. Okay, let's say the question is, this might be, a little, because like you're new to this, so that's super okay. Like it might be too hard to try to get it immediately. Like, the game is, how does row 3 equal a combination of row 1 and row 2. So I'm going to start using some fancier notation like A row 1 plus, and now that I'm getting a little bit more sophisticated and a little fancier, let's use some subscripting just to make things clear about what's what. How does row 3 equal some number times row 1 plus some number times row 2? So, can you find a way to combine rows 1 and 2 to equal row 3? Like, maybe, for example, one that doesn't work is 3 row 1 plus row 2. Like, does this work? No, because 3 times row 1 equals the row 3, 6, 9. And if you add 3 row 1 plus row 2, 3 times row 1 plus row 2, we do get a 7 in the first entry. Like what I'm trying to find is like, how can I multiply rows 1 and 2 and then add them together to equal the third row? So I'm focused on getting 1 and 4 to combine to equal 7. So we got the first number correct, but then 3 times 2 plus 5 is 6 plus 5, and that is 11. 3 times 3 is this 9 right here. And then if we add, if we add 9 and 6, then it's 15. So let me make this even more clear, or a little clear at all. Remember, let me write out, row 2 is 4, 5, 6. And if you add those two together, 3 row 1 plus row 2, 3 row 1 plus row 2, 3 and 4 add to 7, 6 and 5 add to 11, 9 and 6 add to 15, and that does not equal row 3, which is 7, 8, 9. We're trying to get 7, 8, 9. Yeah. Okay, I see it. Sir, I got it. 2 row 1 minus row 2 row 2 minus row 1. Perfect. Exactly. 2 row 2 minus row 1 equals row 3. Good job. Nice job. So what you saw is 2 row 2 minus row 1 equals row 3. Looking at the matrix, it's good to be able to try to do this in your head, looking at the numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9. 2 times row 2, looking at the first column, that would be 2 row 2 minus row 1. 2 row 2 minus row 1. 8 minus 1 is 7. 10 minus 2 is 8. And 12 minus 3 is 9. So, good job. Nice. Yeah. I think that's enough. Yeah. So you saw it. one could write out 2 row 2 minus row 1 the way that I wrote it here. If that's not completely clear to any future viewers, try writing it out this way. What is 2 row 2? And then what is row 1? And then subtract the 2, and then you'll see that it should equal row 3. Okay, so that's really neat, I think. So I will never forget that fact about this matrix. 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's one reason that I love the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9. Anytime I get the opportunity to try an example for myself, I use those numbers. Or numbers like, if I need another one, maybe 1, 1, 2, 2, 3, 3, 4, 4. Or a number like, I don't know, if we need even more examples, I might go to 1, 3, 5, 7, 9. But some sort of pattern that I can bring back, like it's easy for me to remember. It's one of those first simple examples. Like here's a great example of a determinant that equals 0. Now, here's something cool. What's another one to try? When I thought about this earlier today, I was like, okay, well, I know for sure that writing it backwards, 6, 5, 4, I'm very confident that writing it backwards, well, yeah, that's still going to be 0. It's still like you're just moving the columns around, but 2 times row 2 is still going to be row 1, or 2 times row 2 minus row 1 equals row 3. Here's a tougher one. What happens if you write it this way instead? 1, 2, 3, 4, 5, 6, 7, 8, 9. What about that? So there's 2 ways to think of this. We could calculate the determinant this way. And like actually come up with a number that this determinant equals. Spoilers, it also equals 0. So that's one way to try to calculate the actual number for the determinant. Or we could try to, for a moment, be clever and see, is there a way to combine these rows as a combination of one another? Like, oh, what about row 1 plus row 2 equals row 3? 1 plus 2 is 3. 4 plus 5 is 9, which is not 6. Okay. What if we tried the same thing again? 2 row 2, probably, I don't know. I mean, we wrote this matrix completely differently. We wrote it vertically instead of horizontally. That seems like a completely different set of equations, right? This is neat. It works out again. Let me, I'm sorry for the spoiler. But yeah, try that. What if you try the same one? 2 times row 2, so 4 minus 1 is 3. 10 minus 4 is 6. 16 minus 7. 16 minus 7 is 9. What? Wait a minute. What? That's a little unexpected, right? Isn't that cool? Isn't that cool? This feels like a completely different, totally different. But the same determinant. Now, I'm going to introduce a fancy notation. It turns out that the matrix that we totally guessed, like maybe I could write it 1, 2, 3, 4, 5, 6, 7, 8, 9 vertically, that matrix is called the transpose. Like writing rows as columns instead of rows. Like write every row as a column instead. Why does it happen? We'll get there. We'll get there in time. But that is actually a theorem in linear algebra. So this is a place where I think it's very cool to try to come up with examples for yourself. And an easy way to generate examples is 1, 2, 3, 4, 5, 6, 7, 8, 9. And if you don't get what you were looking for the first time, try twisting 1, 2, 3, 4, 5, 6, 7, 8, 9. Maybe you write it backwards like we did here. Or maybe you write it vertically like we did here. 1, 2, 3, 4, 5, 6, 7, 8, 9. And we're still getting the same dang thing. So that's neat. I think that's really neat. Yeah, so there we are fixing the mistake from yesterday, and I will leave it at that in terms of explaining a little bit about matrices and how what we showed earlier was how we could solve this problem that we solved by substitution. This was like strategy 1, substitution. We solved by substitution, and then we solved the same high school algebra problem by elimination. In high school algebra, you will learn those two ideas, that you can solve equations by elimination like this, or by substitution like this. And then I showed this method of elimination we can write really nicely in a matrix. We can do that really much more easily. Somehow this, if we look at just the matrices on the left-hand side of the screen, if we look at those, somehow that, to me at least, feels a lot simpler than this. Maybe it's just because I'm used to it, but over time this becomes simpler, especially if you have 100 variables or more. And we talked about the determinant as the determinant is a function. I keep saying machine, but it is a function that determines if a system is solvable. Cool. And then here we found this really neat trick. In this case, the determinant of at least this one matrix that we tried, is it always true that the determinant of a matrix equals the determinant of its transpose? Transpose is writing as columns instead of rows. Let's keep that in mind, maybe. maybe we go to office hours and ask our teacher, and we're like, I found this really cool coincidence. Is it a coincidence? And then they'll say, oh, I was going to talk about that next week. Good job. And then you get extra credit. Cool. That's it for the... Right now we're at right now we're starting to talk undergraduate first course in linear algebra. That was college linear algebra. We started with high school linear algebra. Then we went to college algebra. I should say high school algebra 2, college algebra, and then college linear algebra. I think that's accurate to say. Now we're going to go to math major linear algebra. We could say graduate linear algebra. Sir, what's going on? Do you have a question? What's also, oh, you know what? Let me take this opportunity. This is a good chance for a break. I tried to get this to work. Yeah. So I got chat. Look at that. I got chat. So you're showing up right here in my t-shirt. What's up? Stand strong. Yay. Let me also do it. Why does it happen? I should have another scene where you're on the left-hand side taking up way more space, but here we can have chat while I'm scribbling around on the left, right? So that's pretty cool. Question? Hey, G Guy, what's going on? New name is good. Good to see you, dude. How are you? Yeah, I like the new name. The Math Hobbyist somehow feels better. Like, I want to separate this a little bit more from my guitar content. Try to have them as separate things. So, I don't know if Stand Strong saw this. I guess I didn't write it here anywhere, but new handle is the Math Hobbyist. What do you think? Stand Strong. What do you think of this new handle? It's clearly in the bottom right of this screen at the moment. Do you like it more or less than the old was JC Practices Math? This was the old handle, and it's because my guitar handle is JC Practices. What do you think? And you said, sir, I guess you don't have a question, right? We'll just move on. So, question to you all. Which handle do you like more? And G Guy, thanks for stopping by. Hit the like button, y'all. I'm stoked to have another practice stream. I think it's more fitting. Descriptive yet ambiguous. Nice. I love it. Yeah. Yeah, I think it's cool. It's like, I think it's descriptive. It says a lot in it. I think it's like, I'm a hobbyist. My only challenge is that it doesn't say practicing. Like, it doesn't say the word practice. A math hobbyist could be showing up with, like, a nicely produced, tutorials. Are my feet on camera? No, they're not good. Like a math hobbyist could be talking about their college classes and vlogging as they go through, or, well, I guess it wouldn't be somebody going through college classes, but it could be somebody vlogging in a different style. This is a practice stream, which is like a concept that, I don't know. There are others doing it, but I feel I'm one of those introducing that idea. Cool. now we're going to jump to graduate linear algebra. We're going to work a problem from Shilov, another problem. So last time we did a really neat first problem calculating the sign of the determinant terms. So here I calculated this determinant explicitly, and what that last problem was about is, for a term, is it going to have a positive sign or a negative sign? Is it going to be on one of the ones that you add or one of the ones that you subtract? For example, this number, 1 times 5 times 9, this one was the entries A11, A22, A33. This one, and this one. Whereas, maybe in green, 249 is this one. This green against cyan is kind of gross. Red. what I got was 249. That is the element A12, A21, and A33. An easier one to see is this one, 357. That is A13, A22, A31. That's a little bit easier to think of. They're like, I don't know. Yeah. I don't know exactly where I'm going with that. Any good book for trigonometry and geometry for IMO? To be honest, don't know. I don't know, but I can try to find out and let you know next time if you keep showing up. My hunch is that for geometry, my hunch is that this book would be good. There's two books that I want to suggest. I've only looked at this briefly, but this one looks pretty good for algebra problems for IMO. And I think that this one would be good for geometry. So, take a look as well. And these are Dover books. They're lovely because they're cheap. Like compared to other more expensive books, these are much cheaper. And they're challenging problems in algebra and challenging problems in geometry. I'd take a look at those. Trigonometry, I don't know if it's accurate or not, but I think that trigonometry can be considered part of geometry. Trigonometry is like kind of it's part of geometry because trigonometry is all about studying circles. Studying circles and studying triangles, like the legs of a right triangle. A right triangle has a very special property, which brings me to an awesome point. Like if I come over here, my other question besides my handle, we have this new handle, the Math Hobbyist. What do you all think of this as the profile bubble, like the little image instead of my stupid smiling face? I'm thinking something like this. If you don't know what this equation is, don't worry about it. I'll explain it in time, but it's similar to the Pythagorean theorem, which is trigonometry. Pythagorean theorem says that the sides of a triangle can be added together in this way. A squared plus b squared equals c squared. very famous fact in math, and that's part of geometry and part of trigonometry. Now, what this fact is saying is that there is no Pythagorean theorem with cubes. For whole numbers. Like, of course, you can put 0, 0, 0. Yes, it's Fermat's last theorem. You've seen it before. Great. So I feel like I think that'd be a cool avatar, maybe. Like, have Fermat's last theorem. A lot of people recognize it. You recognized it. That's huge. That tells me that maybe it's a good avatar. I think that the colors are a little ugly. It could be a different set of colors. It could just be one color. A to the n plus b to the n does not equal c to the n when n is greater than 2. Like, imagine, I'm drawing a circle around it so that you can imagine what it would look like in a circle avatar. It's a great avatar. Good. Because I think that this is lovely because a lot of people do recognize it. Okay, thank you. Thanks for the feedback. Linear algebra, let's wrap up today. So, again, what we are asking is, the last problem was trying to calculate these signs. Like for this term, A13, A22, A31, is that going to be positive or negative? And yeah, that's the sign of a term in the determinant. Cool. They provide good color combination. Yeah, I think that multiple colors is better than one color. I think maybe it kind of hints at all this iPad stuff going on too. I don't know. Okay, so we calculated the sign of a term to be -1 n I1 I2 ... ij. That's what we calculated, and we found a couple of examples, and we found that the sign was positive for both of them. I could repeat that exercise with a simpler three-dimensional matrix, like the matrix that we did earlier, but I just want to move on now. Shilov 1.3 is still talking about determinants. Oh yes, you have a question. Like a question came to write 1 to 9 numbers in a 3x3 grid where set of multiplication of rows and columns come the same. Okay. Let's see. And they told to derive for an n by n grid. I'm not sure if I followed the question, to be honest with you. Are you... So we already did do an example where the rows had a linear combination. They can be expressed as a linear combination of each other. Is your question to find one where it doesn't? I would twist the numbers ever so slightly, like 1, 1, 2, 3, 4, 5, 6, 7, 8, 9. How do we know that we're done thinking about examples? Like, I bet that if we try a bunch of examples, we won't be able to find a way maybe like these two added together, those two added together add to 11, but 5 and 8 add up to 13. 6 and 9 add up to 15. So that adding rows 2 and 3 doesn't work. Okay. See the grid. If we okay, so the question is, if we, correct me if I'm not copying your example correctly. My iPad is frozen. Okay, we're back. If I understand correctly, you are writing this matrix 6, 5, 4, 7, 3, 2. If we multiply rows and columns, we get the same set of numbers. Well, if you multiply... I'm not sure if you're saying that 1 times 8 times 9, like multiply this row across equals 6, 5, 4, and that equals 7, 3, 2. That's not true, because this is the only one with a prime 7, for example, whereas this one doesn't have a prime 7. So that's not... Oh, I miswrote the second one. 6... Why did I do 6, 4, 7? I meant to write 6, 5, 4. That's not what you're saying, I don't think. Multiply rows different. Yep, no. Yeah, we get... Okay, so if you multiply these, I haven't checked, other than the first one, you're saying that they are 72, 120, and 42. When we multiply the columns... Oh... Huh? Are you serious? Really? Multiplying the columns, 8, 5, 3 gives you 120 as well. And 9, 4, 2. No, that... Okay, 9, 4, 2 does not multiply to 42. Yeah. 9, 4, 2, 36 times 2, we got 72. Yeah, it's 72. Okay, so I don't think that this leads to anything like multiplying across or multiplying vertically. I could be wrong, but I don't think that that leads to any structure. So, I mean, that's a great question, though. That's a great thought. And I could be totally wrong. We have 6... Okay, so you got 6, 7, 42. Yeah, 6 times 7 is 42. Okay, so let me write it this way. Great question. I love taking questions like this. You're saying that when we multiply across, we're getting... multiplying across, we got the number 72, 120, and 42 when we multiply it across. And then when we multiply vertically, let's use white, I don't know. Yeah, when we multiplied vertically, we found 72, 120, and 72 again. Right? Yeah, I mean, that's really neat that we got 72 and 120 again. But 42 doesn't match 72. That's what I'm trying to say. Like the third row, multiplying across the third row doesn't match multiplying the column. Oh, did I? The third column multiplying vertically, 9 times 4 times 2 is 72, right? Yeah. 6 times 7 is 42. Oh, wait. Oh, shoot. Oh, yeah. No, what am I talking about? Yeah, you are absolutely right. Why did I did have a little brain fart. That is 42. Interesting. Okay, yeah, there we go. Now things are starting to make sense again. See, I'm going to make a lot of mistakes here. 42 matches that 42. That 120 matches this 120 matches this 120, and this 72 matches this 72. Interesting. I think that this is a coincidence, and it's a coincidence that 6 equals 3 times 2, and 8 equals 4 times 2. That's my guess. But I don't think that that's always true. Try to come up with some more examples. You might be right, and I'm forgetting a reason for that in linear algebra, but I don't think that that's always true. That's really neat. And so that is a problem about using... Oh, okay. So is it always true? That is in your homework. Neat. So, I'll have to think about this separately, I think. I don't think I'm ready to try to prove this one. But you're saying that for any, let's see, for an n by n matrix, let's get a couple examples. A1I equals the multiplication of a j or a1. This one should be a j. A1j, like multiplying across the first row and each of the different columns equals the last row, or the last column. What am I talking about? AI for every row, the last column. That's one example, and now I think that the general statement here is that from j equals 1 to n, a for any aij equals the product of I equals 1 to n ai, and then here I think that we're going to have n plus 1 minus 1, or n, I don't know, something like n minus something. I'm not ready to prove it. Where the prime numbers put it into the grid. Yeah, I'm just surprised that. Okay, so 7 being a prime number. In this case, 7 is a prime number, and it happened to be fixed. Like in the first column, it's also, it's in the first column and it's in the last row. But then if we swap those two rows, 6, 5, 4 here, like we're going to get the same result, right? 7, 3, 2. But in this case, it's in the second row, first column, as the only thing that matters is the elements of the set, so we cannot fix the coordinates of rows nor column. As 7 is a prime number and can only occur in one row and one column, it depends where the prime number is put into the grid. Yeah, good question. I don't know. Yeah, the short answer is I don't know. I think I need to see the exact problem statement to be able to like try to tackle proving it. I'm not ready to try to solve that right now. Let me keep thinking on that, because that's where is that a homework set from your teacher? Is it preparing for the IMO? Is that an IMO challenge question or yeah, please do share the problem statement. Like the exact problem statement would be very helpful. But for the sake of this video, I'm going to continue now. But then if you give me that problem statement, I'll think about it afterward. And I think after another cup of coffee, I might be able to get it. So, neat. That's really neat. Let's keep going in Shilov. And I want to state this next exercise because I gotta go. I gotta go very soon. And I want to solve this problem because I thought it was fascinatingly cool. So we're going to use this fact. It's really cool. Review. A couple of videos ago, I showed that the sum of the first n numbers is n plus 1 divided by 2. And we proved by induction. So that's all I'll say there. We're going to use that fact in this problem statement. Shilov 1.3. With what sign does the term A1n, A1n minus 1, or A2n minus 1, AN1 appear in the determinant of order n? Cool. I had to scratch my head for a second to figure this one out. Now we recall that the sign of this term, which I'm going to call A, the sign of the term A is going to be -1 times n I1 ... IN. Now, challenge here is that this assumes standard form a I1, so it's all the terms are ordered by the columns. So we're going to multiply all the terms by columns. So the first column, and then some other row, the second column, and then the last column. But again, these rows are not in order. Like, they could be mixed around in the matrix. A-I-N-N. But, so, if we call this A, which has, like, kind of some weird problems to it, like, maybe let's call this, I'm going to use good old trusty X. Let's use good old trusty X. Like, maybe we multiplied all those terms together and therefore, like, I don't like using A because it's a multiplication of a bunch of separate A's. But X is not in this standard form. So we need to rewrite X in that standard form. Notice that we have it backwards. A1n, X was A1n, A2n minus 1, dot, 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 A n1, right? So what that is if we think about it geometrically in terms of the matrix, it is, I think, always that? Nope. Yeah. Something feels off. But, gotta go to dinner. Yeah, good to see you, man. Thank you for stopping by. It is such a pleasure to hang out and chat while I'm doing this. It's a brand new concept and idea, so it means a lot that you're enjoying it. Hit the like button and hope to see you again soon. Thanks. Let's wrap this up as quickly as possible. We need to rewrite X in this form. X, now, we just need to write it backwards. Because, again, remember that multiplication is commutative. In linear algebra, we assume that you can multiply two things, A times B equals B times A. Here, so we just need to write it from the right-hand side. A-N-1, A-N minus 1, 2, dot, 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 A-1-N. Now we can analyze the number of inversions of this sequence. 1, 2, dot, dot, dot. Oh, wait. Nope. We are analyzing the inversions of the rows, the row coordinates. So n minus 1, dot, 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 1. Recall that we can think of the inversions as the number of times that a larger number appears before a smaller number. And, well, n is going to be inverted n minus 1 times. The n minus 1 term is going to be inverted n minus 2 times. N minus 2. This n minus 1 is the yellow inversions, and then we've got the n minus 2, and then we've got a bunch more, and then finally 2 is inverted once. Like the number 2 is inverted once. 2 is before 1. So n minus 1 plus n minus 2 plus ... 1. That is so close to the theorem that we proved before about 1 to n. But now we just are adding up to n minus 1. It's an easy proof to see that that is n times n minus 1 divided by 2. So, therefore, the sign that we're looking for is -1 to n minus 1 divided by 2. And we're done. You can take this a step further and say that I think it's if n is 1 or 2 mod 4. If n is 1 or 2 mod 4, then the sign is positive. And if n is 3 or 4, I believe I got that right, then the sign is negative. I think that that's correct. If, for example, n is 4, then we have 2 times 3. Oops. Okay. Well, it's something like this. Just got off by 1, but we're very close on that. That's it for today. Thank you all for watching. It is a pleasure to be practicing linear algebra again and to be hanging out with folks while I do it. So thanks for watching. Hope to see you again. We've done 2 linear algebra lectures or practice sessions now, and soon we'll probably do 1 more linear algebra practice session. I'll try to find some more computational examples for next time. I'm glad that we did get a matrix calculation today. So this is the kind of book that I was looking for, like a book that is really showing more kind of calculation. And I think I have a good idea. I think I'm going to pick up string in order to do, to practice more undergrad linear algebra. So we'll do 1 more linear algebra lecture practice session next, and then we might jump to calculus. So tomorrow linear algebra, day after calculus, and then we'll come back to number theory. I think that's going to be our cycle. It's going to be linear algebra, or really algebra in general, number theory, calculus. And we're just going to keep going back and forth. Maybe recreational math as well. I don't know. We're figuring it out as we go. Thanks for watching. I am the math hobbyist, and I hope to see you again soon. Bye. Great to see you stand strong. Thanks for